Hey there, and welcome to the next video on triple integrals over general solids. We're going to do definition 6.2.1 and example 6.2.2. The volume of a solid S is given as the triple integral over S of the function 1 dv, or if we don't want to write the 1, the triple integral over S of dv, which is a completely corresponding analogous result to the area of a region, which was the double integral over that region of the same function 1 dA. Example 6.2.2. Let S be the part of the first octant bounded by the planes 3x plus 2z equals 6 and 3y plus 4z equals 12. We're asked to set up the integral or integrals that represent the volume of S as a type 1 and a type 2 solid. There's a, oh no, I read it wrong, as a solid of type 1 and type 2. The wording is fine. So let's go and sketch, first of all, what these planes look like and get a handle on what the solid S looks like. So 3x plus 2z equals 6. We only need the first octant, so let's graph that. We're going to go by intercepts here, and if we let x equal 0, well then z is 3. And if we let z equal 0, then x is 2. And there is no y component, and so that plane is actually what we would have called a cylinder. It is parallel to the y-axis. So there's the first plane. Now our second plane is 3y plus 4z equals 12. We're going to do the same thing. Again, we only need the first octant. We're going to go by, I really should be labeling my axes, x, y, z, x, y, z. We're going to go by intercepts again. And so if we let y equal 0, z is 3. So that gives us a little hint that maybe their planes are going to meet at that point. And if z is 0, then y is 4. There is no x in this equation, so the plane is parallel to the x-axis, and so our second plane looks like this. Now we can imagine we've got one plane coming out like this. The other plane is going to be coming out like that, right? This plane. And so they are going to meet somewhere in the first octant. I've gone a little bit high here. Let's bring that down. So if I draw the first plane, it starts at z equals 3, goes down to x equals 2. I'm really not good at labeling. X, y, z. We know that, so this is again 3, the other goes out to 4 here on the y-axis. This plane comes out like this. This plane comes out like this. And they meet when x is 2 and y is 4. So that's the point 2, 4, 2, 4, 0 down in the x, y plane. And then this is, they're both flat. And so they are going to be meeting at a straight line when they meet. And so we have sort of a slanted pyramid where the face here in red is the equation 3x plus 2y, no, 3x plus 2z equals 6. And the face here in blue is the plane 3y plus 4z equals 12. So there is our solid. This is our solid S. Now we're asked to set up the volume, so we want the triple integral over S of 1 dV. So let's imagine this as a type 1 solid. That means we need a bottom surface. Well, the bottom surface is clearly the xy plane if we're in the first octant, and then a top surface, and that's a bit problematic. We have 2 top surfaces. So here it is. We'll set this up as a type 1. As a type 1, well, our projection, our shadow down into the xy plane is going to be this rectangle down there. And the rectangle has a top edge of y is equal to 4 and a side edge, that's obviously not to scale, of x is equal to 2. So that's the point here, 2, 4. And if we imagine this boundary here being projected down, it's going to be right there. So our boundary is going to be this line, which is the line y is equal to 2x. And above this region here, let me actually maybe shade, above this region that I'm shading in red, the surface is the red plane, this plane here, that is the upper surface. If the region that I'm shading in blue, this region here, above that is the blue surface, is the top surface. So we've got to split this up into two parts and take the union of them. So let's call this part 1 and part 2, region 1 and region 2. So the region 1 is x is going from 0 to 2, y is going from 0 to 2x, right? If we go in a y, we're going from 0 to 2x, 0 to 2x, and the z is going from the xy plane up to this red surface. And that red surface, we need to solve for z. So if we take the equation here and we isolate z, we're going to get z equals, divide everything by 2, 3 minus 3 halves x. So z goes from 0 to this 3 minus 3 halves x. But that's only half of the region, right? We need the second half as well. X is also going to go from 0 to 2. Y now goes from 2x to 4. So 0 is less than or equal to y. Nope. 2x is less than or equal to y is less than or equal to 4. And over that region here, the z goes from 0 up to the blue surface. So we need to solve for that blue surface. That's this equation here. And if I isolate z, I'm getting z is equal to, divide everything by 4 this time, 3 minus 3 quarters y. So we have a 0 is less than or equal to z is less than or equal to 3 minus 3 quarters y. And so if we want to have the volume of S, we need to take integrals over both of these regions and add them together. So we're going to have the integral from 0 to 2, integral 0 to 2x, integral 0 to 3 minus 3 halves x of 1 dv, plus the integral from 0 to 2, integral 2x to 4, integral 0 to 3 minus 3 quarters y of 1 dv. That is set up as a type 1. Obviously, having to split it up over two regions and add integrals together is suboptimal. So let's see what happens if we set things up as a type 2. So type 2, we're looking for front and back. So we're looking for a front surface. Well, the front surface is going to be in red. And the back surface is the xy plane. And so that, yz plane, the yz plane. So if we draw the projection back into the yz plane, I'm going to label this time. I should have labeled last time, x, y. The yz plane, we can see the projection back there. It's that triangle right there. So we have this triangle down in the yz plane, and that triangle has equation. Well, this is when z was 3, when y was 4, and that turns out to be exactly the same equation that we had up here, that we have z is equal to 3 minus 3 quarters y. And so we can set this up as y is from 0 to 4, 0 to 4, there you go. And z goes from 0 to this function here. So 0 is less than or equal to z is less than or equal to 3 minus 3 quarters y. And lastly, 0 is less than or equal to, now we're in the x direction, x is going from the yz plane, which is x equals 0, up to this surface in red. So I need to take this equation that we used last time, solve for z. Now I need to solve for x. If I do that, I'm going to divide everything by 3. So I'm getting x is 2 minus 2/3 z. So 0 is less than or equal to x is less than or equal to 2 minus 2/3 z. And so now my volume as a triple integral is going to be the integral from 0 to 4, the integral from 0 to 3 minus 3 quarters y, the integral from 0 to 2 minus 2/3 z of 1 dv, and dv is dx dz dy. That's the order that we went in, which makes me look back in our first. I wrote dv, but we know the order that we went in. That order is given sort of here backwards, z, y, x. So that really should have been dz, dy, dx, and again, dz, dy, dx. So just because you can set it up in one order doesn't mean that that is the most efficient way of doing it. In the next video, we're going to evaluate the volume and learn about average values over this same solid S, and we're going to choose to do it as a type 2 solid for, obviously, for efficiency. It'll be quicker to set it up and evaluate it as a type 2 than it would as a type 1.